Hi, my name is Drettakis. I'm going to be presenting my ERC Advanced Grant FUNGRAPH. The motivation that we had in this project was that we can capture scenes very easily for computer graphics, but the geometry is not very good. And while we can use image-based rendering, for example, to display, it's hard to modify, and the quality isn't always good. On the other hand, synthetic scenes can be created, but they're very hard to actually construct. And the standard rendering, while high quality, isn't adapted to the uncertain content. So the high-level goal was to rethink the fundamentals of computer graphics, bringing together the ease of capturing content and high-quality rendering for all kinds of scenes. And the methodology is first to understand uncertainty in computer graphics, so uncertainty in the input, for example, in the case of captured content we saw before, and uncertainty in rendering, both for traditional and IBR techniques. And as a second step, we use deep learning, so somehow marry deep learning with graphics, so that deep learning can help us model and overcome uncertainty and develop more robust and generic solutions. I'll be presenting 4 examples, the first to illustrate how we understand uncertainty. The third and the fourth will be showing how deep learning can help. So the people who did the real work are obviously my students and postdocs and external collaborators. The first project involves global illumination effects, and most notably very complex paths, which we can see here, with highly indirect, diffuse, and specular behavior. The way we address this problem is to store pre-computed glossy probes in a grid and then reproject them during runtime. The main components of this approach were using specular path perturbation theory to look up in the probes which have uncertain content, and the multi-level gather also helps us find inside the probes the information that we need, and then a second 2-step reconstruction that corrects for reprojection error. As a result, we get very good quality at interactive rates compared to the ground truth. We're better in quality than real-time path tracing, which has problems with temporal artifacts. The second case where we're studying uncertainty involves real-world captures, which in particular cars, which have a problem of the fact that cars are omnipresent, but they're very hard to reconstruct, and as a result, since they're missing geometry in the windows, and reflections are complex to render. And the method we developed basically was based on the idea of addressing this uncertainty by improving the car and window geometry, where the information is very uncertain from capture, generating reflections in the novel views by extracting reflection information. And our results are of quality which compares well to state-of-the-art techniques. In the second aspect of our methodology is marrying learning with graphics, and there are 3 main principles. The first is to use geometry as much as possible, then use rendering to help learning, and learning to help rendering, and use synthetic training data for difficult disentanglement problems. So the first such example is using deep learning for relighting, and we see here a scene which we captured at a single lighting condition, and we're able to relight it synthetically. The main difficulties are removing shadows, also being able to resynthesize new shadows, here for example, and changing the overall illumination in the scene. The way we did this is by using first a set of neural networks to take the geometry constructed from multi-view stereo, which gives us shadow maps, which we then refine, and a second network that actually performs the relighting. And the key to this is to use synthetic renderings on which we run multi-view stereo, and that gives us 2 representations, the ground truth and the approximate, so the network can learn to infer this from real scenes. And this allows us to remove the limitation of static lighting in image-based rendering, and to be able to relight scenes interactive. The last example is material capture. And in this case, we started from an initial solution where we have one image, and we can infer an SVB-RDF, and we noticed that by adding several images, we can improve the overall capture of roughness. The key to doing this is by using synthetic materials, then using a parallel set of networks, and then this is used in a rendering loss, where rendering is used to train the network to learn to extract SVB-RDFs that result in very high quality extraction of materials for many different types. In current and future projects, we're investigating deep material capture, so capturing appearance of entire scenes, neural rendering for synthetic scenes and for improving image-based rendering, and of course, all these neural radiance field representations that will be used for these problems and for neural lighting. Thank you for your attention.